Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
So the next topic is numericals on Francis turbine. So we've already seen the derivation of work done, the efficiency. Now let's see a few numericals on it. So let me read out the question once again. A Francis turbine is operating under a head of 60 meter, which is running at 420 rpm. If the outer diameter is 0.9 meter and the inner diameter is 0.45 meter, discharge is radial. Determine the vane angle at the inlet and outlet. So we have to calculate the value of theta and phi. If the flow velocity is constant, if the flow velocity is given constant, means it is same at inlet and outlet both, which is equal to 12 meters per second, and the hydraulic efficiency is given as 80%. So since we are given with the value of diameters, we can calculate the velocity of blade, that is u1 and u2. And we all know that since it is a Francis turbine and the discharge is radial, the velocity of whirl at outlet is 0. So the velocity of blade at inlet and outlet can be easily calculated by using the formula pi d n by 60. The diameters at both the ends are given as 0.9 meter and 0.45 meter. The RPM is given as 420. So you get the values at 9.9 and 19.8. So after you get these values, let's draw the velocity triangle for this particular question. And since we know the hydraulic efficiency, let's use it and get the value and try and get the value of inlet and outlet angle and vane angle at inlet and outlet. So this is how the triangle will look like. Now let's use the hydraulic efficiency formula and get the value of the whirl velocity at inlet. So the hydraulic efficiency is given, the whirl velocity at inlet is unknown, the inlet velocity of the blade is 19.8, G is 9.81, H is 60. So once you rearrange the values and get the value of VW1, so it comes out to 23.78 meters per second. Now let's do one thing. Let's draw the inlet triangle a little bigger and use trigonometry and get the values. Now if you use trigonometry in this triangle, the smaller triangle is, as you can see, so you can get the value of theta easily because we know what this length is, what the value of VF1 is. So opposite upon adjacent is known. So use tan theta and get the value of the theta. So tan theta is nothing but opposite side, which is VF1, upon the adjacent side, which is VW1 minus U1. So tan theta is VF1 is given in the question 12. VW1 we already calculated 23.78 minus U1, which we have calculated as 19.8. So once you solve this, and you will get the value of theta as 71.65 degrees. So this is the value of the vane angle at inlet. Similarly, you can observe the outlet triangle. This is the value phi. So U2 is known. V2 is nothing but Vf2. As I said earlier, the vertical component of the absolute velocity gives you the flow velocity. So it is already vertical. So V2 is nothing but Vf2, which is 12. The value of U is known at outlet. The value of U is 9.9. So again use same relation tan of phi is nothing but opposite side, which is Vf2, upon the adjacent side U2. So the tan of phi is Vf2, which is 12, and U2, which is 9.9. So you get the value of phi once you solve this, and it comes out to 50.48 degrees. So we've got the values of theta and phi, which the question was asking about. So that was all about this question. Let's see the next question now. A Francis turbine having overall efficiency of 80%, hydraulic efficiency 90%, produces 3000 kilowatt power under a head of 140 meters running at 1000 rpm. The speed ratio is 0.9, flow ratio is 0.3. We have to find the guide blade angle at inlet, the diameter of the runner, and the width of the runner at outlet. We have to assume that the discharge is radial, which means the value of beta is 90 degree in the velocity triangle. So the speed ratio is 0.9, which is nothing but u upon under root of 2gh. So the value of u comes out to 47.16 meters per second. So we got the value of u. Next, the question is asking about diameter. Since you know the value of u, you can easily get the diameter. So the d comes out to 0.9 meter. So using the value of u, which is pi dn by 60, u we calculated and we got 47.16. We got the diameter. Next, use the given data again, where the speed ratio we use, the flow ratio is given as 0.3. Flow ratio is nothing but Vf upon under root of 2gh. So Vf is nothing but 0.3 times under root of 2gh. The head given is 140 meter. So once you solve this, you get the value of Vf, which comes out to 15.72 meters per second. Again, since this is a Francis turbine, Vw2 is 0, the wall velocity at the outlet is 0, and let's use the hydraulic efficiency formula, which is Vw1U1 upon GH, and the hydraulic efficiency is given as 90%, so 0.9. Vw1 is unknown. U, we have already got the value of U, that is 47.16. G is nothing but 9.81, and the value of head, which is given as 140 meters. So once you rearrange the values, you get the value of whirl velocity at inlet. And once you solve this, you get 26.2 meters per second. So after getting the whirl velocity, let's move on to the triangle to get what the question asks is the angle at the inlet. So let's draw the inlet triangle first of all. So the Francis turbine inlet triangle looks something like this. This is V1, this is VR1, this is U. And let's observe the value of U is 47, the value of whirl is 26. So the value of U is more than the value of whirl. So the triangle that I've drawn is not valid, so we have to draw a new triangle. It will look something like this. So you have to draw the triangle very carefully. You have to see which one is bigger, U or Vw1. If Vw1 is more than U1, the triangle looks as I've drawn on the left side. If the value of U1 is more than Vw1, so the triangle looks like I've drawn on this side, on the right side. So now let's calculate the value. So this is theta. So I have to calculate the value of theta. So this angle becomes 180 minus theta. So once you use trigonometry, tan theta in this triangle, so tan of 180 minus theta is nothing but opposite side, which is the flow velocity, upon the adjacent side, which is nothing but u minus Vw1. So the flow velocity I've already calculated, which is 15.72, and the value of u also I know, which is 47.16, and Vw1 is also known, 26.2. After you solve this, you get the value of 180 minus theta as 36.87 degrees, and once you shift the value of theta on that side, bring 36 on this side, you get theta as 143.13 degree. This is the guide vane angle at inlet. Now for outlet, you have to draw the outlet triangle. For outlet triangle, the velocity, absolute velocity, is equal to the flow velocity. Now you've calculated theta, now this is phi. So use again tan phi here. Tan phi is nothing but opposite side upon the adjacent side. Adjacent side is the value of u. So opposite is the flow velocity at outlet, and the value of u here. So once you substitute the value of flow velocity is 15.72, the value of u is given as 26.2, so you get the value of phi. You get the value of the guide vane angle at the exit. Now the last part is the question is asking about the value of width at the outlet. So before going on to width, let's calculate the discharge first. If we know the overall efficiency, let's calculate the discharge value using overall efficiency formula. So overall efficiency is nothing but the power output upon rho g QH. So the overall efficiency is given, the Q value is unknown. The question has also given the power developed, which is 3000 kilowatt, which is nothing but 3000 into 10 raised to 3. Rho is the liquid used as water, so the rho comes out to 1000. G is 9.81. The value of head given is 140, and the overall efficiency given is 0.8. So once you calculate all these values, you get the value of discharge. So the discharge comes out to 2.73 meter cube per second. Once you know the discharge, you can get the value of the width. As I said earlier, Q is nothing but area times velocity. Area is circumference into width, so pi d into width into the velocity. And the velocity that has to be used is the flow velocity, because here in Francis turbine the flow velocity is the velocity which is responsible for creating discharge, which helps to give discharge, and the whirl component is the velocity component which helps to give the motion or the momentum, or it helps to give power to the runner. So the flow velocity is nothing but the velocity which helps to give discharge, and the whirl velocity is the velocity which helps to give momentum to the runner. So the value of Q we've calculated as 2.73. Now the question is asking about the width at the outlet. So the discharge is nothing but area times velocity. Area is pi dB into Vf. All the remaining values are known except for B. So you can get the value of B and substitute the values, known values, and get the value of B. Once you rearrange and solve, the value of B comes out to 0.06 meter. So in terms of mm, it comes out to 60 mm. So that is the value of the width of the runner. So that was all about this question. Let's move on to the next question now. So I'll read out the question once again. The external and internal diameter of Francis turbine is 1.2 meter and 0.6 meter respectively. The head on the turbine is 22 meters, and the velocity of flow through the runner is constant, and it is equal to 2.5 meters per second. The guide blade angle is given as 10 degree, and the discharge is radial at inlet and outlet. So in other questions, the discharge was radial only at the outlet. Here, it's a special question in which the discharge is radial at both the inlet and outlet side. So the triangle will have a bit few changes in it. So we have to find the speed of the turbine, the vane angle at the outlet, and the hydraulic efficiency. So let's draw the triangle first. So here the discharge is radial both the side. So as you can see here, the velocity is having a radial discharge at both the side inlet and outlet. So U1 becomes equal to VW1 and VR1 equals to VF1. V2 is VF2 and the discharge at the outlet side is always 0. VW2 is 0, we know that. Next, so let's see what the given data is. The flow velocity is given, the velocity of flow which is constant, so Vf2 is equal to Vf1 is equal to 2.5, but we know that as you can see in the triangle, Vf1 is equal to Vr1, so Vr1 is also 2.5, V2 is also 2.5. As you can see from the triangle, we can make it out. Next, the velocity of flow we've got. Now let's use trigonometry in the inlet triangle. This angle is alpha, so let's use tan alpha and see what we get. Tan alpha is nothing but opposite upon adjacent, so opposite is Vf1 upon the adjacent side is U1, so U1 comes out to Vf1 upon tan alpha. And the alpha value is given at the inlet side, which is 15 degrees. So the value of U1, once you divide these two, you get U1 as 14.178 meters per second. And as you can see from the triangle, U1 is equal to VW1, so VW1 is also equal to 14.178. Now since you've got U and the diameter is given, you can get the RPM. The diameter is 1.2 meter, it is given in the question. 1.2 into RPM is unknown. On solving, you get the value of RPM as 225.65. Now let's calculate the velocity of the runner at the outlet. U2. U2 is nothing but pi d2n by 60. So U2 is unknown. Diameter at the outlet side is given as 0.6 meters. And the RPM we have already calculated, which is 225.65 divided by 60. So you get the value of U2 as 7.09 meters per second. Now we've got the value of U1 and U2. Now if you want to find the vane velocity at the outlet, let's use the same tan concept over there. Tan of phi is nothing but opposite upon adjacent. The opposite side is Vf2 upon adjacent is U2. Vf2 the value is 2.5, U2 we have just calculated 7.09. After you simplify this, you get the value of phi as 19.4 degree. So you got the value of phi. Next, the question was asking about the hydraulic efficiency. So the hydraulic efficiency is nothing but VW1 U1 upon GH. So the value of VW1 is nothing but the same as U1. So you can write U1 square upon 2 GH. Hydraulic efficiency is VW1 U1 upon GH. In this question, the value of UW1 is same as U1, so you can write U1 square upon GH. The value of U1 is 14.17, so it comes to 14.17 square upon 9.81 into 22. So the hydraulic efficiency comes out to 0.9314. So if you want to write in terms of percentage, it becomes 93.14%. So we've calculated all the things that the question was demanding. It was asking for speed of the turbine, we've got the RPM. So it was asking for vane angle at outlet, we've got the value of phi. So it was asking for hydraulic efficiency, which is 93.14. So it's all about the question. Thank you.